Okay, welcome. So what we're going to do in today's lecture is we're going to be using some of the tools that we'll be using to solve kinematics problems. Now, this is going to involve some graphs and then some equations, and then we'll talk about the one of the specific situations that comes about quite often. So those are the three things we're going to talk about today. All right, so I need to share the notes. Okay, there we go. And cool. All right, so the two basic types of tools we're going to be using are going to be the what I'll call the kinematics graphs and the kinematics equations. All right. Now I'm going to start with the kinematics graphs because really, I think interpreting these, I think if you can interpret the kinematics graphs accurately, I think you can get a pretty good understanding of what the physics is trying to tell you. And the kinematics graphs are not limited to constant acceleration. You can construct kinematics graphs knowing just a little bit about the situation. And a lot of times you can construct one kinematics graph from another one. And we'll talk about how that works in a little more detail. All right, so first one to talk about is so we'll do graphs first. And the first one to talk about is going to be position time graphs. Now, basically what you're dealing with when you're dealing with position time graphs, and I'll sketch these. I want to show you some kind of constructed ones, but a lot of times being able to sketch them is kind of helpful. So basically the way a position time graph works is you basically do a one quadrant graph and you put t, a lot of times you indicate the units in parentheses on one axis, and then you put position. Again, I'm going to use X as a symbol for position. And then you put that on the vertical axis. And basically what you would be doing here is you can split this bottom axis, X axis into intervals. Same thing with the Y axis. And then you can just draw where the object was. So let's say the object started at 0. And then let's just do a real quick, easy one where it's basically like going up one X unit for each time unit it's going up. And these, it could be 1 meter and it could be 1 second, whatever, it could be other things. But basically what you have here is you could then, construct either a best fit line or directly connect the dots. In physics, we generally construct best fit lines. We don't connect the dots. Not always, but that's just a general thing. And then what you have is you have this sort of connection between position and time. Now, why do we care about this? Well, first of all, it does give us a visual representation. So we can kind of describe what's going on. We can say, well, we could, basically from this graph, we could say the position is increasing linearly with time. That would be a way we could describe that. Now, the other thing we can do is we can find delta x from this. So let's say we want delta x being the displacement, as we recall. So delta x from t equal 2 to 5, we'll say. Okay, so this would be 2, 3, 4, 5. Now what we can do is we can go up and we can say, okay, at t equal 2, we can just go up there and we can go over, and then that is x equal 2. So we could say at t equal 2, x equal 2. So that would be, t initial would be 2 and x initial would also be 2. And then we could go up at the 5. So t final would be 5. That's basically given to us. And that means that we go up to the graph and we can find our x initial, and I don't think I did these intervals quite right, but we could find our x final rather. And that turns out to be right at 5. So x final equals 5. Now, what we want to do is we want to say, okay, delta x equals x final minus x initial, which is just 5 minus 2. So we can find our delta x this way. Delta x is 3. All right. Now, if we were going the other way, if we were going down, we could do something like that too. So you can visually determine what your displacement is. You can also determine your velocity as a reminder. So velocity is just delta x over delta t. We already got delta x, and that was equal to 3. Delta t was equal to t final minus t initial, which would be 5 minus 2, which would also be 3 in this case. Now, basically what this means is v is going to be 3 over 3, which would be 1 meter per second squared. Now, again, as a reminder, this was average velocity. Now, hopefully what you notice, and the main relationship to know from this graph is that v, and I'll star this, and I'll do something a little different. V is the slope of the position versus time graph. Okay, so this is one of the most important things to remember if you're looking at this graph, is that your velocity can be determined from this graph by looking at the slope. Okay, so that is, if you're trying to analyze these graphs, being able to have that relationship in mind is a very important thing to do. Now again, hopefully you can find the slopes of this, but the relationship between velocity and position time graphs is kind of important, not only because it does relate these two quantities, but a lot of times in physics, the slope of a graph of some graphed quantity is something relevant that you might want to know. Okay, so for instance, like if you were talking about like an energy usage versus time, that slope would give you a power, would give you some kind of a power rating. So that's something to keep in mind when you do this. Now, the other thing about this is you can imagine if we had an x versus t like this, and this is again beyond the scope of our course, but if we had an x versus t and it looked something like that. So it's constantly changing positions as time goes on. Basically what can happen is velocity can be found by finding the slope at any point on the graph. Now, what's cool about this is we clearly have a changing velocity. Like this slope is changing. In that first graph I drew, the slope was basically the same. This graph, it's clearly changing. And what this means is we could approximate it just by drawing the slope. Okay, or just by figuring out the slope. So, there's no readings here, but let's say I wanted to know the slope right here. So I want to know what is V right there. Well, basically what I could do is I could draw some little line that's kind of, this is now a line that has roughly the same slope as the graph at that point. And then I could find the slope of that line, and that is equal to V. Okay, so that's kind of an important thing that we can do. The next graph to talk about is the velocity time graph. So this is the second graph, velocity time graph. Now, these velocity time graphs tend to be a little bit simpler, though again, you can have them be quite complicated. Like for instance, the graph I just drew, if we were to do velocity versus time, that would be kind of a complicated graph. But what you can do, again, it's similar in setup, but you just have a velocity and a time, like so. Now, I'm just going to do something that's constant velocity. So basically what a constant velocity would be, 4, 5, And then, we'll just do 1, 2, 3. We'll do it something like this. Basically, a constant velocity is a horizontal line. Okay. So constant velocity. Now, what this is saying is that v equals 3 no matter what time is. Okay. Now, in this case, the velocity is also not changing. So finding things finding things that are that you find things like delta v and acceleration. Turns out this graph has no acceleration. We'll talk about that in just a second. But one of the things I wanted to show you is that delta x if v equals 3. Now you can think about this. You might be able to figure this out. If you're going at, and we'll just say it's meters per second and seconds here, if v equals 3 meters per second. Well, delta x is just going to equal v times delta t. Okay. Now, the way you can think about that is one that just kind of makes logical sense with what you know about speeds, but that's a rearrangement of this formula. Delta x over delta t equals v. Okay. And I'll do without the vectors for now, since we're just working in one dimension. So you multiply t by both sides of that, then that's what you get. Well, as a reminder, if we had our delta t from 2 to 5 again, we could say this was our delta t. Well, our velocity is just equal to 3. So our basically, if we wanted to get the delta x, we would know that delta x would be equal to 3, and then delta t was equal to 3 times 3, which would be 9. Well, one of the really cool things about that is represented on the graph in a visual way. So if you think about that, and we draw in this rectangle, right, like so. The height was 3, and that was equal to the velocity, and the change in time was 3, and that was just equal to the delta t. So the takeaway here from this graph is that delta x, the displacement, is the area under a velocity time curve. Okay, so that is another key thing to know about these graphs and about the relationships they describe. All right, so important thing to take away there. Now, if we have, say, something like this, where we have a velocity that's changing. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And again, it's not perfect, but let's just say we started at 0 at time t equals 0, and then we're going up to 1, then 2, then 3, then 4, then 5. And what we have here is we have, basically a linearly increasing velocity. So what we know now is we know that the velocity is increasing. Well, one of the things we can say, and I'll do this below, is that the acceleration is the slope of the velocity time graph. Okay, so the reason why that's the case is what we have here is we have, so we might have, V1 and then V2. Well, this distance between the two is going to be delta V. So delta V is just going to be V2 minus V1. And then we go down, and then our delta T would be right there. So delta T is going to be, we'll call that T1 and T2. Going to be T2 minus T1. And then A is just going to be delta V over delta T. Well, again, that's just the rise over run of this graph. So this can be a really useful thing if you're trying to find acceleration from these graphs. Okay, so that's something to keep in mind. So these two ideas that the area, and I'll box this in orange as well. The area under the curve is the displacement, and the slope of the graph is the acceleration. This is what makes the velocity time graphs very useful tools. Okay. Now the last graph is acceleration time graphs. These are less useful. We'll talk about them, but they're not as useful as the other two, mostly because their slope doesn't tell us something we're generally interested in. It gives us a kinematics quantity called jerk, which we're not going to talk about much. But basically what you'd have acceleration and then time on one axis. Now, you could still 1, 2, 3, 4, 5, and we'll just go up to 3 here. Now, what you might have with acceleration is you typically would have a constant acceleration, but what you might get is you might get initially you've got some constant acceleration. Like for the first 3 seconds, you'd have an acceleration of 2, and then your acceleration would drop down to 0. So basically, you'd have like a step function of your acceleration. So a equal 2, and then after that, a equals 0 over here. Well, the main thing to take away from this is that if you're accelerating at 2 meters per second squared for 3 seconds, your velocity changed by a total of 6 meters per second. Okay. So each second, an acceleration of 2, and I'll put units here, meters per second squared in seconds. An acceleration of 2 meters per second squared says that each second your velocity changes by 2 meters per second. If you do that for 3 seconds, well, so that if that delta t was 3, then your total delta v would be equal to 2 meters per second times 2 meters per second squared times 3 seconds, which is equal to 6 meters per second. You'll notice the units actually cancel out on that one. Well, your delta v is equal to 6 meters per second. Once again, that is just the area of this thing that we drew right here. Okay, so that's the delta v. It's another thing to keep in mind is the area under the acceleration time graph curve. Okay, so the slope, it gives us, like I say, it gives us something called jerk. We're not going to go into that. But the other thing to remember is that the area under the curve can give you your change in velocity. Okay, so that's kind of a useful tool. Now again, I think these tools are super useful. I'm still kind of on the fence as to how much I'm really going to quiz on these tools, but I do think they are worth knowing, and they can be quite helpful. All right. So the next thing I want to talk about is the kinematics equations. And these tend to be the bread and butter that get taught in kinematics. Now, important thing to know, kinematics equations. Important thing to know is that these are, they assume constant acceleration. Okay. So that is really important. Now, if you don't have constant acceleration, you can't really deal with them. Now the other thing to know is that 5 quantities are used in these equations. Now they're not all used in a single equation, but basically it's a family of equations, and 5 quantities are used in the equation. So basically it's a relationship between these equations describe relationships between these 5 quantities given constant acceleration. Okay. Now the 5 quantities I'm going to give you, because almost always you're going to need to identify the quantities that are given and the quantities that you need from this list in these problems. Okay. So t is going to be now sometimes you could do it as either t or delta t. Really, this is going to be a time interval. That's really what it means. Now, in a lot of these kinematics equations, they do just express it as time. But for kinematics, you're always considering a beginning and an end. So the t you're using there is actually a time interval. So I do want to indicate that you will see the t symbol occasionally, but it's talking about an interval of time. Okay. Now, the second quantity is going to be delta x. As a reminder, that is displacement. The third quantity you're going to need is going to be V sub I. And I'll occasionally write this as V naught. This will be your initial velocity. The fourth quantity you will need will be V final. Final velocity, V sub F, final velocity. And the fifth quantity that these equations will use will be A, which is the acceleration. Now, again, basically what these problems involve. They involve you being given some of these, not all of them, and figuring out which equation or equations you need to use to find one or more of the other ones. Okay, that is really fundamentally what this is about. So these equations are not hard. The thing that most people struggle with is figuring out which equations to use. And the issue is that I don't think people have a clear conception of the goal. So if you can think of the goal as you have some of these quantities, sometimes the challenge is figuring out which ones you have and which ones you don't have. Like that's not always clear. But then the goal is to use these equations I'm going to give you in order to find some of the other ones. If you think about it in those terms, a lot of times it becomes clearer which equation you need to use and the best strategy you have for doing that. Okay. So the first equation, equation one. Now, a lot of times there are only three kinematics equations given. I like to give more than that. So that's why I'm going to I'm going to do this. It's your average velocity. There are actually two average velocity equations. And so I guess that's something I didn't include here. Yeah, actually, I'll include that as a sixth quantity. So I'll say 6. And the reason is I just want you to know these equations. V bar is your average velocity. Now, the important thing about V bar, there's a couple different ways it can be expressed. All right. First of all, it can be expressed as just your displacement over your time. Okay. So I'm going to write delta t. That's kind of how I learned it. Again, sometimes you'll see this is written as just t, but there is equation one, and that is your V bar expressed at delta t. Now, equation two. The important relationship is actually the combination of equation one and two, because V bar, if it's constant acceleration, it's basically an average of your initial velocity and your final velocity. So V naught plus V final over 2. Okay. Now, this is really important. All right. This is quite an important relationship. And really, the important equation is kind of a combination of these two. But I wanted to define it. It's delta x over delta t can be written as V naught plus VF over delta or over 2. Sorry. Okay. Now, again, this is just average velocity. Now, again, only works if your acceleration's constant. But the idea here is that if your acceleration's constant and you add the two velocities together, divided by 2, you've taken the average. So it's basically the middle velocity between those two extremes. Now, by definition, your change in displacement over change in time, or your displacement over change in time, is equal to your average velocity. So I include this sixth quantity, average velocity, You don't really need to ever use it. You just need to know that this relationship is true. Okay. So I'll actually call this equation 1A and equation 1B. And then this one would be equation 1. All right. So this first one is the equation that's more important to use. All right. Equation 2. Not question mark 2. Um, and this is going to be your acceleration equation. All right. Now, basically, this is one that we've already talked about. Um, and we had acceleration was defined as delta V over delta T. Well, a lot of times instead of doing it this way, you just remind yourself that delta V is V final minus V initial. And then the way this ends up getting written, so you have acceleration equals V final minus V initial over delta T. You end up multiplying by delta T on both sides. And what you get is you get V final is equal to A delta T plus V initial. So this is the second equation right here. First equation, and notice how I related it back to the 5 initial kinematics quantities that I gave you. So that's kind of what's going on there. Okay, so this is if you're not given displacement, you're just given your velocities, your acceleration, then you can use this equation. Now, equation 3. This is your um call this your displacement time equation. The derivation of this one is a little bit harder to see, so I'm not going to go too far into the derivation of it. I don't know that we're really going to have time to do that. But basically, what you have here, you can actually, if you wanted to do this, you can actually prove that this is the case by looking at a graph, kind of like this one, and reminding yourself that the area under the graph is equal to the displacement. Um, but you'd have to have an initial velocity, so it'd have to be translated upward a bit. I may do that at some point in the future. But again, that's more of a derivation. You just need to know the equation is what's more important. Okay, so what this is delta x equals 1/2 a delta t squared plus v naught delta t. Okay, that is your displacement time equation. All right. Now, when you think about the fourth equation, um, equation 4, this will be your acceleration or your displacement velocity equation. And actually, the way I'm going to put this one, this is the time independent equation. So there is no time in independent. It's the only one without time in it. And it looks like this. It's V final squared equals 2A delta X plus V naught squared. Okay. Now notice there's no time in that one. So the idea here is that all of these equations are tools for a given job. Now you'll notice there are 4 quantities in each one of these equations that I've given you. So we look at the first equation. 4 of those I guess 6. Really, it's 5 because we kind of we got rid of average velocity by combining these first 2 equations. But you'll notice this one. This first equation, it has 4 of those 5 quantities. So it's delta x, delta t, v naught, and v final. No acceleration. So the idea here is if you were given a problem where you knew it was constant acceleration, but you didn't know that acceleration, and you were given 3 other quantities and you were asked to find the fourth, you could use this equation. This one, again, has 4 quantities. This time it's velocity, final velocity, initial velocity, acceleration, and time. All right, that's equation 2. So this one is if you didn't have displacement and you weren't interested in finding displacement, you'd want to look at this second equation. Okay. The third equation, what you're given is delta x, delta t, a, and v naught. And that's what this involves. So you'd use this equation if you didn't have your final velocity and you weren't interested in finding your final velocity. That's the idea. This fourth equation, you have v final, v initial, a, and delta x. This is what you would use if you didn't have time and you weren't interested in finding time. Okay, so basically, again, these things are going to be different tools for different situations. Now, I think I'm going to record one more lecture in which we go over some example problems looking at these things. Where the lectures and the tools are coming at you kind of fast, so I think it'll be useful to have an example, a few examples to look at as well. So I'll record that sometime soon. All right. So those are the 4 equations. Last thing I want to talk about is free fall. And basically what free fall is, it's a special type of kinematics. Now we'll get into free fall a couple of as we do 2-dimensional kinematics as well. But for free fall, the really important thing to keep in mind is that basically what we're saying is that we are dealing with an object that has an acceleration downward due to gravity. Now, it's important to know that due to gravity. It's important to know that this isn't just saying that gravity is operative. Basically, it's saying that the object is accelerating maximally downward to the extent that gravity will let it. So the idea is that you're experiencing gravity right now, but unless you're currently watching this lecture while jumping out of an airplane, or maybe just jumping off off a wall or something, you're not in free fall, okay? Because there are other things acting on you that are counteracting gravity. In my case, it's the chair I'm sitting on, so on and so forth. But if you're dealing with free fall, what you are saying is you are saying something about your acceleration. So what this means is your acceleration equals, and the signs can vary. A lot of times what you do is you say acceleration equals 9.81 meters per second squared downward. That's the way to put it. Okay. Now the symbol we use this lowercase g to be 9.81 meters per second squared. So a lot of times what we'll say, if we say down is negative, which is most common, because that's how you think about like a y-axis, down is negative. In physics, it doesn't have to be. You could let down be positive. And if you were only moving in the downward direction, that might be convenient because then you wouldn't have to have a negative acceleration, a negative velocity, and a negative position. You could just make all of those positive. But if down is negative, we say acceleration would be equal to negative g. If down is positive, then we say acceleration is equal to g. All right, so you may have seen this before. Sometimes you'll see physics texts that say g is equal to negative 9.81. I think this is a mistake, okay? G is a constant, all right? The negative indicates direction. So this is something that's true about a lot of times in physics, is that a negative sign indicates direction. Now, the point with physics that I just tried to make is you can always change which direction you decide to be positive. You think about it, you're just looking at it from a different perspective. You're kind of looking at the situation like you were on your head, and then down would be up, and you could say, oh, I'm just gonna analyze it that way. And the point is that the math still works out. So attaching that negative to the 9.81, I think, is a mistake, because it's saying that you're always going to let up be positive, and that's not always useful. we'll let a lot of throughout this course, we'll let a lot of different directions be positive. Not, it won't always be up, it won't always be down, it won't always be left or right, it might be slanted in some way. Okay. So the point is that if you are in free fall, one of the quantities that one of the kinematics quantities will be known. It will be your acceleration will be g. Okay. And what this ends up meaning is it ends up meaning that you end up using the last three equations quite a bit because acceleration is a known quantity. You don't end up using the first equation because you already know g. And since this equation doesn't use g, that first equation tends not to be as useful in free fall. Okay, so that's just something to keep in mind with that. But like I said, I will go, I think I will record another lecture and post it at some point um about the just some examples of how to go about doing this. Okay. So just keep that in mind. I hope that will be helpful. I don't really want to do it here because this lecture is getting a bit long, but these are the main tools that I think you will need for kinematics, and that you should have using these tools should be able to get you what you need from in order to do the assignments as well. So in the next lecture, we'll go over a couple of example problems. And I also do want to take a look at at the ranking task from the homework, not only because I think it's helpful to understand what's going on in that ranking task, but also it'll help you with the quiz as well. Okay, so I'm going to go ahead and end things there. Thank you for joining me. I will see you in the next lecture.